All right, so motivated by special relativity, we've introduced these three dot products into planar geometry. We're calling them blue, red, and green. The blue is the usual Euclidean one. The red and green are relativistic dot products. Now, I want to introduce complex numbers. Okay, so complex numbers are algebraic devices that allow us to solve all manners of equations that we can't so easily solve without the square root of -1. And they were, of course, developed slowly. People were reluctant to admit them because of the dubious, perhaps, nature of what these things really were. But eventually, by the 19th century, mathematicians had grown comfortable with them, and they appreciated the way that complex numbers help us with rotations in the plane and in general geometry in the plane. So the strong link between the Euclidean geometry in the plane and the usual complex numbers was well established. But in the 19th century, mathematicians also started to investigate other alternatives, other algebraic structures. And in particular, I point to the work of J. Cockle in 1848, and then William Clifford, and many more, introduced variants of complex numbers. Okay, and in some sense, these variants of complex numbers play the same relation to the ordinary complex numbers as does the red geometry to the blue geometry. Right. So these are sort of algebraic manifestations of special relativity long before the physicists actually had discovered special relativity. So the mathematicians were investigating the complex numbers that are associated with such a geometry. And these numbers have been discovered and rediscovered many, many times since that time. And so there is a plethora of names for them. They were originally called tessarines, I think, by Cockle. They're also called split complex numbers, sometimes hyperbolic numbers, double numbers, space-time numbers, and probably one could add another half dozen different names for the same essential object. So we're going to introduce them here in the context of the triality of chromogeometry that we've been talking about. In other words, we're going to introduce blue, red, and green complex numbers. So this triality is not part of the usual story. It's my preferred way of thinking about things, but I think it's a very good way of thinking about things. So we're going to introduce the blue complex numbers. Those are just the regular complex numbers. Okay. We're going to introduce red complex numbers, which are essentially things that have been called these names by many people, and other names as well. And then we're going to introduce green complex numbers too, because we want to preserve this threefold symmetry that's going on here. And I'm just going to suggest that instead of calling them blue complex numbers, red complex numbers, green complex numbers, we might also occasionally call them just blue complexions, red complexions, green complexions. Just a name I toss out there as a possibility, okay, to add to this big list of names that we already have. But it's especially important, I want to emphasize the threefold symmetry that's really at the heart of things here. And I'm going to adopt a somewhat different point of view than most of these people. So for us, there's a course in linear algebra. We're going to try to find these things in the context of linear algebra. So even if you have studied regular complex numbers before, you might see them today in a new light. All right, so for brevity, we're going to use this notation. We're going to define C sub B, C sub R, and C sub G. So these are blue complexions, red complexions, green complexions, or blue complex numbers, red complex numbers, green complex numbers. We're going to define all of them inside 2 by 2 matrices. All right. And here's what they are. So the blue complexions are the matrices of this form. A, B minus BA. Where A and B are now unrestricted. When we were talking about isometries, we saw that matrices of this kind, where A squared plus B squared equals 1, were the isometries of the blue dot product. Now we're going to be a little bit more general and say, oh, we don't really need isometries. Let's just consider general matrices that have this particular form. A, B minus BA for A and B, any rational numbers. I remind you that I always work over the rational numbers, all right? Real numbers are some fantasy. There's no need for them. So we have our feet firmly planted on the earth here, right? So rational numbers is all we need. Red complexions. We're taking our lead from the Lorentz transformations that occur in special relativity. So we're identifying this kind of matrix and calling it a red complexion, something of the form A, B, B, A. But now without necessarily the condition that A squared minus B squared equals 1. A and B can be anything they want to be. And finally, the green complexions, or green complex numbers, matrices of the form A, 0, 0, B. Again, taking our lead from the isometries that we had on the previous page, but now not having necessarily the condition that A, B equals 1. A and B can be whatever they want to be. All right, so we have three different, essentially, subspaces of 2 by 2 matrices. Each one of these defines a subspace. All right, so let's just think about that for a second. If I take two matrices of this form and I add them, I'm going to get another matrix of this form. If I take a matrix of this form and I multiply it by a scalar, I'm going to stay in the space. So it's closed under addition and scalar multiplication. That's a subspace of the 4-dimensional space of 2 by 2 matrices. I hope it's kind of obvious that it's a 2-dimensional subspace because it has an obvious basis, namely the identity matrix and the matrix 1 minus 1. Here is a different 2-dimensional subspace of our 4-dimensional space of matrices. All the matrices of the form A, B, B, A. It's another subspace. It's closed under addition, closed under scalar multiplication. And similarly here, another 2-dimensional subspace of the 2 by 2 matrices, just the space of diagonal matrices. This subspace is particularly simple and familiar in some sense. All right, so the claim is each is closed under addition, scalar multiplication, and also multiplication. These are more than just subspaces. They're, in fact, subalgebras because they're also closed under multiplication. If we take any two matrices of this form and we multiply them, we're going to get another matrix of this form. Same thing for these ones. Same thing for these ones. And here I've just spelled that out very clearly so you're convinced of that. Here's a matrix of this form. Here's another matrix of this form. Here's the product. And you can see by looking at the product that it has the same form as this one. Namely, this entry is the same as that entry. And this entry is the negative of this entry. Same thing for these matrices. If we take two of them, multiply them, we can see that we get another matrix which has the same form. This and this are the same, and in this case this and this are the same. And much more simply, this is also a subalgebra. Here are two matrices of that form. Their product is also obviously of that form. This is a lot simpler to check than these two. All right, so these are blue complex numbers, red complex numbers, green complex numbers. Now you're probably thinking, wait a minute, aren't complex numbers things of the form a plus bi? Where is the a plus bi here? Well, let me show you. If we look at this product here, the blue one here, right? If we look at this product, we can see that this matrix is really determined by that top row, right? If you know that top row, then you know the bottom row as well. And so if we take these two matrices and look at their top two rows, then the product of the two matrices gives us a new top row. So since these matrices are completely determined by their top rows, this matrix multiplication is determined completely by this new product of this vector times this vector equals this vector. And here is essentially the more familiar complex numbers that perhaps you're used to, that AB times A prime B prime is AA prime minus BB prime, and AB prime plus BA prime. That's the more familiar vector form of complex numbers. We can do the same thing over here in the red context. Also, if we're working in the red complexions, then one of these matrices is determined by its top row. And so these two top rows determine these two matrices. When we multiply them, we get a new top row over here. And so we can think about this matrix multiplication as just this vector times this vector equals this vector. A lot like this one, except that there's not a minus sign, there's a plus sign there. Otherwise, very similar. And okay, over here, it's a little bit different. Here, the vector is sort of that one there. We have to peel off that diagonal. If we think of that diagonal as forming a vector, and there's another vector there, then each of these two matrices is determined by those diagonal vectors, and then their product is that diagonal matrix. So yes, also here we could interpret this purely in terms of a product of two vectors, giving us a third vector. Okay. And so we're going to be doing that shortly, but I want you to appreciate that the multiplication is really coming from this matrix multiplication. Okay. We can sort of just restrict our view to only the top row and say, oh, we're just multiplying this vector times this vector equals that vector. But what we're really doing is sort of ignoring this larger, more beautiful matrix multiplication, which is really driving the algebraic structure uniformly in all three cases. All right, we're covering a lot of ground here. All right, this is packed full of information, this lecture. In fact, most of the lectures in the last few have been like that. So please take your time, go slowly, right? Don't hurry it. Be patient. Try to absorb things slowly at a time, and be prepared to spend quite a few hours on each one of these lectures before you go on to the next lecture. Okay, there's a lot of information to be absorbed and to be pondered, especially because a lot of it will be unfamiliar to many of you. Okay, so let's have another look at these three different types of complex numbers that we've introduced in the context of 2 by 2 rational matrices. Blue complexions, red complexions, green complexions. Kind of rolls off the tongue in a pleasant way. All right, so AB minus BA. Let's observe, as we did before, that this is a two-dimensional space, which has a natural basis consisting of these two matrices. So we can think about this matrix as being a linear combination of the identity matrix and this particular matrix. Let's call this matrix 1. Okay, let's call it 1. And let's call this matrix I. Then we can write this as A times 1 plus BI. And we could, in fact, just then forget about the 1 and just say A plus BI. The algebraic structure is really encoded in the fact that this matrix I has a particular property. If you square this matrix, you get minus this matrix. You get minus 1. So this is a matrix answer to the question, what is the square root of minus 1? Is it some weird thing that's coming from Andromeda? From a linear algebra point of view, it's not weird at all. It's very simple. I is that 2 by 2 matrix. Nothing more and nothing less. The intimate connection between this and rotation by 90 degrees or a quarter turn, is obvious from its form. If you think about this matrix as a transformation of the plane, for example, if you multiplied with the row vector 1, 0, you get 0, 1. If you multiply by the row vector 0, 1, you get minus 1, 0. That's exactly a rotation by a quarter turn. So it's no surprise that complex numbers are intimately connected with rotations of the plane, because we're building them from 2 by 2 matrices, which are all about transformations of the plane, or can be interpreted to be that. So that's how we recover the usual high school approach to complex numbers. But we can, at the same time, now that we've just done that, we can just do the same thing for the red complexions. ABBA, this Lorentz kind of transformation type matrix, is a linear combination of the identity, and this new matrix 0, 1, 1, 0, which we might call J. So J is 0, 1, 1, 0. And J has the property that J squared equals 1. Not minus 1, but 1. Okay, please make sure you appreciate that. So this J squared is 1. If you square this matrix, please check that you get this matrix. Okay, so what we're doing here is recovering one of the ways of describing these tessarines or split complex numbers or double numbers. So they're often written as expressions of the form a plus bj, where j is some symbol whose square is 1. And maybe you're left with this question, what does j really mean? Okay, well, here I'm telling you what j really means. Okay, j is that particular 2 by 2 matrix. Nothing more, nothing less. So it gives a completely concrete, down-to-earth interpretation of the split complex numbers, or the double numbers, or the hyperbolic numbers, or whatever you want to call them. But we don't want to leave out the green complexions. Okay, they're also part of the story. Somewhat more neglected part of the story from the algebraic point of view, because perhaps people think, oh, the diagonal matrices, it's too simple or something like this. But it's also sort of interesting. So here is your typical green complexion, A00B, and we can write it also as a linear combination of 2 basis vectors, but in a slightly different way. So here's the identity matrix as before, and here's a new matrix. Let's call it K. Why not? So K is 1, 0, 0, minus 1. And then the coefficients that you have to use here, you have to be a little bit more careful, even though it's sort of a more elementary situation in a way. Here you have to use a plus b over 2, and here you have to use a minus b over 2. So please just check that when you add these two, you get an a there, and then this bottom entry here will be a b. So in terms of symbols 1 and k, we can write this as a plus b over 2 times 1 plus a minus b over 2 times k. And k squared equals 1. So we are meeting these 4 basis vectors of the 2 by 2 matrices. But wait a minute, haven't we seen these before? Yeah, we were talking about these before, but we hadn't given them names before. This is the identity matrix. This is I, this is J, this is K. But wait a minute, this was also the matrix that was the symmetric matrix encoding the blue dot product. And this one was the symmetric matrix encoding the red dot product. And this one was the one encoding the green dot product. And this one here was that skew symmetric matrix that was a little bit outside the others, that was encoding parallelism of vectors. Okay, so here's a fun exercise for you to get used to those matrices I, J, and K. So verify that we have the following relations. These are relations between 2 by 2 matrices. That I times J equals K. That K times J equals I, and that K times I equals J. And furthermore, that Ji, if we invert the order here, then we get minus K, that Jk equals minus I, and that ik equals minus j. Now some of you will know about the quaternions and may have watched, for example, one of my famous math problems series on quaternions. I think it was 13. These are looking like quaternions because we're using the same symbols, but they are not quaternions. Okay? They are subtly different. These rules here are subtly different from the quaternion rules. And I'm going to give them a new name. Okay? We call them dihedrons. Okay? We're going to talk about them more at some later point, but you can perhaps try to figure out why that's a reasonable name, that they're intimately connected with a dihedral group. Think about symmetries of a square. Okay, so what we've done here is we've started with these blue complexions, red complexions, and green complexions. And I've shown you that, in fact, we could encode such a matrix more efficiently by just recording the top row. And we can encode this matrix more efficiently just by encoding the top row. And we can encode this matrix more efficiently just by encoding the diagonal AB. Okay. So when we do that, we could then just rewrite the multiplication of such objects just in row form. Right? So AB times A prime B prime equals AA prime minus BB prime AB prime plus BA prime. And in some treatments of complex numbers, this is essentially how one proceeds. One defines the complex numbers to be basically ordered pairs of numbers, like AB, and then one defines the multiplication by this rule. It's sort of like a rabbit pulled out of a hat. And the addition is just component-wise, so if you add these, then you get A plus A prime and B plus B prime. Okay, so we can do the same thing here with the red complexions. And again, this is basically formulas that we've seen before. I pointed them out before. If you multiply this matrix times another one, then you can rewrite the product just in terms of the top rows as AA prime plus BB prime, AB prime plus BA prime. And you can do the same thing for the green ones where things become very simple. Just the product of this vector times this vector is just the pointwise product. This is exceedingly simple for the green complexions. So addition is component-wise, scalar multiplication is component-wise, and multiplication is also point-wise for the green complexions. All right, so one could, and in some cases, especially for the regular complex numbers, we could introduce multiplication like this. But then one has some work to do. Then one has to prove the usual laws of arithmetic in each case. For example, you have to prove that multiplication is commutative, that's associative, that it distributes over addition. It's not entirely obvious why that should be. And one can then do the same thing for the red complexions and the green complexions. It's not too hard for the green complexions because of the simple structure, but for the red complexions and the blue complexions, there's some work to be done. But notice that from our 2x2 matrix approach, this is unnecessary because we know that with matrices, these laws of arithmetic already hold. We know that matrix multiplication is associative. We know that it distributes over addition. Commutativity, well, that you have to check. That's a special consequence of the fact that we're just restricting ourselves to these particular two-dimensional subspaces. But generally speaking, a lot of things are somehow conceptually clear if we frame everything in the space of 2x2 matrices. We're going to see that even more next time, where we're going to explore this algebra of 2x2 matrices in greater depth and develop some more complex number arithmetic, but not just in the familiar blue context, but in these other two as well. We're going to do things sort of uniformly between all the three colors. And we're going to see that nice aspects, algebraic aspects of the complex numbers, even in these more unusual settings, are naturally linked pleasantly with interesting algebraic relations in the 2x2 matrices. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.